in the program, we are moving on now to our last session of the day, the so-called lightning talk session. What is a lightning talk? A lightning talk is a 4-minute short presentation about work that is going on, has been going on in the last couple of months, that is an idea or a current new developed feature. We had a total of 16 fantastic lightning talk ideas that were presented, of which we can show 14 today. And without much ado, we'll get started right away with the first one by Lazzaro Alonso, with Marco Bernazzocchi being on deck for the next one. Lazzaro, take it away.
Thank you. So thanks for having me. So why Julia? Several reasons, but I will just name a few. It's built for scientific computing. So that means that from the beginning, it was built for speed. So Julia is fast. And another features is like you have multi-threading, multi-processing, and GPU support, and even TPU support as well. So that's one of the reasons. The other reason is that it composes. So the code that you produce can be used by another user to improve their packages. The next reason is that Julia is written in Julia, so you don't need C or C++. And every user can be a new contributor, a real one, because you don't need to learn C or C++ to contribute to the ecosystem. And the most important part, I will say, is that the philosophy is not only to make code that machines execute, but rather code that other humans can understand as well. So for me, those are the big reasons to use Julia. In the geo space, you could start by loading data with these packages that are provided by the Julia community. And to explore your data, you could use Mackie.jl, which is my favorite package for visualization. So once you have your data, you could start producing this kind of animations already, like the impact of the asteroid 65 million years ago, or the temperature and precipitation around the globe. Or even more, you could put your raw data simulations all together into a nice animation.
1 minute. Oh, sorry, no. 1 minute and 43, I'm sorry.
Yeah. The last part is for big data. So if you want to show 20-meter resolution animations, you can also do that. Or you can even do aggregations of millions of points on the fly. And lastly, dashboards. You can combine all the performance of Julia to create dashboards, where now our aim is not just to have data visualization, analytics, and visualization again, but also going back. So create your dashboard and trigger the loading of the data, the visualization, and the analytics on the fly. Thank you.
Okay. So now we have Marco Bernazzocchi from OpenGIS, and he will talk to us about efficient ground truth thanks to QField. No?
I can do that if you want, but that's the next one.
Who are you?
I'm Marco Bernazzocchi, but I have 2 talks.
Oh, you have 2 talks, so you start with the other one. So the importance of seeding in open source. All right, thank you. Go ahead.
Cool. Yeah. Open source and seeding, why it is important and why you should work in open source. Well, the first and most important thing is wherever you're working at, being an institution, being academia, being a company, you need to try to create an environment that fosters creative thinking, because people that are motivated are going to be the ones that create the best ideas. Open source itself, some people do not know what it is. And so it is a really good thing if in your organization you do have some champions that will try to push people toward it, will explain to them what it is, why it is good, why it is the best way to develop software. If you are an organization, a company, whatever that is using open source, remember that there is nothing bad in paying for the most important asset that you have in your company. If you're using and relying on some code, support it. Be it by giving it developers, be it by giving in time in documentation, in use cases building, or by giving in money. There is absolutely nothing bad in writing checks to open source projects. And I'm stressing this because the open source world is really bad in doing that and in telling you that is an important point. But we also do have little boxes that need to be filled. We also have employees that need to be paid. So really, that's an important part to consider when you're going into it. There is nothing about being, open source is not about only being for free. It's about being the best way to develop software. If you are creating open source software, do not just think of it only as a project, as your project. Do not just write code. Try to build a community behind it, because if it's just code, it will not survive. If there are people that are behind it, it will grow and thrive. And when you're building a community, try to be fair. Try to push people to be better than you. You might have been the one that started the project, but you want to get better people than you in your group, because that will make sure that your project gets growing and better. At a certain point, your project might be so relevant that considering engaging with bigger umbrella organizations like OSGeo or OGC, or if you're not in the geospatial world, I'm sure there are other organizations like this. Engage with them, try to get more people into your own community, because this will just make your software product or your community even more relevant. Last but not least, again, consider reaching out to industry partners to help you out building a more solid product, to help you out building better code, having more time to spend on building it, having more people, more resources, making your project better. And most of all, keep on seeding, keep on having new ideas, try to keep on pushing these ideas, because if you give time and commitment to something, eventually this little seed will turn into a tree. In my personal experience, 10 years ago, I needed 3 more credits for finishing my master's. And I decided to start a little side project that turned into the most downloaded and highest reviewed application for field data management, with almost 1 million downloads nowadays. So from 3 ECTS to 1 million downloads, just because back then I decided to make it open source. Thanks.
Thank you, Marco. You're up again. So next, we have Marco telling us more about QField from QGIS. And on deck, we have Alejandro Coca Castro from the Alan Turing Institute. Thank you, Marco.
Good. Supposed to be at 5:40. Tonga, 7th of January 2022. Everything was almost quiet. There was a little bit of pre-eruption activity going on, but nobody imagined that a week later, huge ash clouds, a big tsunami would cover most of the islands of this island state. It was the biggest eruption that happened in the modern history of Tonga, and here they had a problem. They had a situation where their main industry was very hard hit. Tonga relies a lot, of course, on farming, and a tsunami and ash clouds are not really the best for farming. The good news was that they got a lot of high-resolution satellite data very quickly, so they could assess what happened. The question was, well, what was the situation before? Luckily for them, they had started in the 3 years previous to the eruption to map their own country with QField. QField, the application I mentioned before, allowed them to go out in the field of all the islands with over 3 years with different campaigns with around 100 people and digitize a data set that included around 12,000 parcels across the land related to what they were producing. They had high quality attribution, so they had pictures, they had videos of the plantations, they had attributes of what were they producing, when were they producing, what value was, and they created maps in QField itself or in QGIS where they could analyze what was happening. And when the hash clouds, the tsunami hit, they were ready. They had the data that told them what was their ground truth before the event. They were able to very quickly analyze what they had before and through remote sensing what they have now to decide where they needed to go and put most resources that were coming in with all the international aid. This allowed them, of course, to be very quick and very fair in where to go and support. The tool they're using, QField, is, as I just mentioned before, I'm going to repeat myself now, is an open source tool made for field data survey. It doesn't really matter what data you want to collect. Here they decided to do all their farming. Later on they decided to do also fisheries and other subjects. And when the tsunami hit, there is a quote from one of the Ministry of Fisheries that says, well, the eruption severed the cable that brought internet to Tonga. Because QField is made for online and offline work, they could still keep on working with the maps that they had offline and be able to go out in the field and really check, okay, I'm here, there should be a huge plantation here, and what do I have now? Just the breeds. This farmer needs our help as soon as possible. This farmer was a little bit luckier, it might get help later on. So QField, really cool application, obviously really proud of it. Get it, try it, it suits any kind of data that you need to ground truth or to just go and get in the field.
Thanks very much, Marco. Now we have Alejandro Coca Castro from the Alan Turing Institute. I will talk about SciVision, making computer vision more accessible to Earth observation, followed then on deck by Codrina Maria Ilie from Terrasinia.
Hi everyone, I'm here today to present SciVision. It's an initiative that was incepted at the Turing. And essentially, SciVision aims to solve real-world challenges and democratize computer vision methods to support the interdisciplinary and international researchers. One hand, we have the developers of these computer vision algorithms, that there are many out there. And of course, there are many domain-focused applications, and as well, we have data providers, people who are now creating benchmark data sets. And at the end, we are trying to build a community that is trying to connect them and trying to establish good practices, how to share scientific computer vision models, like similar you can find in the industry. SciVision as well is a catalog, and we are aiming to have a catalog where people have models, and we know this model, which kind of tasks you can perform. And we have data sets, benchmarks, and we are also trying to use some images that you can fetch from a stack as well, and trying to give more visibility. People who have this data set, they can explore and try to run models that are from other domain to, in this case, air observation. And we have as well an API, and this API you can run in 5 lines of code. I cannot show here. But this particular example is one of the use cases that we have is a model that was trained to map roads and infrastructure in the UK using historical maps. And thanks to SciVision, it was discovered dead and was repurposed to do plant phenotyping. And this person, that is a colleague at the Turing, she's analyzing these kind of images and repurpose that patch-based classification for that. SciVision also aims to be an ecosystem of other software that aim to help computer vision tasks, and that's why I mentioned TensorFlow. And I guess one of the challenges that we have in computer vision is when you have this post-processed or outputs of computer vision model, you want to extract features. And we would like that TensorFlow is connected to SciVision in order to create workflows that you can share with others and not doing, again, the same workflows. I mean, like extracting like the number of objects, the area, and so on. So we are working as well to create an ecosystem. And in the future, we are aiming to expand our use cases. So I see we have many AI applications. So super resolution is one of them. If you have this kind of tasks, you are welcome to explore the SciVision website that is in the slides, or contact us in the Turing email account that we have for that. Another kind of task that we are aiming to tackle is object tracking. You will see there's some example for that. Shape identification, because if you start seeing air observation data, for instance, I have colleagues that are working with bioimaging, and they have one kind of data that they call cryo-EM. It's very noisy, it looks like SAR images. So this kind of interdisciplinary, and try to see and discover these models from this domain and try to repurpose to air observation, that will be interesting. And that's the vision that we are aiming to democratize this model. As I said, you can run through API that in only 5 lines of code, you can explore what you can potentially then scale up with resources.
30 seconds.
We are looking as well at kind of applications, so you are welcome to contribute. As I say, we are a community and we are expect to grow. Just to mention, the API is building on existing open source software stack like Pangeo. We are using XArray to try to handle n-dimensional data sets. We are aiming to exploit SAR data set in the future to storage and help to provide support to big data sets. And as well, in terms of models, we are aiming to apply a good license and good practices of that. Thank you. Yeah.
Thank you. So next we have Kodrina Maria Ilie from TerraSigna talking about your open source resources platform, OSS4Geo. And on deck we have Mariana Damova from Mosaica.
Thank you. Hi, everyone. So I'm here to very shortly and fast present to you an initiative that I've been part of for some time now, since 2016. And in the last year, we've actually convinced ESA to give us some funding because it started as a volunteer initiative. The title is pretty pretentious, like Open Source Software for Geospatial Resources Platform. But I would like you to think about it as a metadata curated catalog of open source tools for any kind of geospatial related activity. I mean, any kind of processing, visualization, storage, so on and so forth. So the basic idea is that this open source ecosystem is an extremely dynamic ecosystem. In 2016, when I first started this idea, I had the very naive impression that being part of the open source community since university years, I know pretty well how this ecosystem looks like. But it was not true, because in the following years, we have ended up documenting almost 400 open source applications. The idea is that we very quickly understood that to do this in a very useful way for the community, we needed to have some resources in order to build an operational, let's say, infrastructure, because at the beginning, the way that we were documenting was in a Google spreadsheet, because we wanted to make it super simple for people to add information. And we used a D3 library to make this fancy graph. But since then, a long time has passed, and now we are in a much better shape. We have still a few months of contract with ESA, so we can improve what we've done so far. So any kind of feedback would be super useful for us. I'm not going to go through slides. I would prefer to show you what we have done so far. So this is how our graph looks like at this point, but everything that we've done since 2016 and within the project is, we like to say, well documented on the project website. We have a clear statement on why we want to do this, how we see this working in the future, because one of our main goals, ultimate goals, is for this project to live beyond this, of course, this contract, and we have plans on how to do that, because after we've put everything together, we want for everything that we've documented and everything that we've developed to be under the umbrella, let's say, of an open source foundation, and we've already been talking with OSGeo to, let's say, to take over. I will not go too much into detail. Maybe you have a bit of time and curiosity to go around and look. Of course, we have a governance model for what we want to the way that we want this project to be governed. The contributions are very important for the actual sustainability of our project and of the initiative. And I don't have much time, so I'll just go back and show it to you maybe. Now it's in beta. Everything that you see here documented is done by the implementation team. Of course, everything developed, everything used is open source. The documentation, the data itself is open licensed. We are offering it through an API. So if you want to play with it, you're more than welcome to do so. We have some filters within this visualization, but feel free to move around and have a look. The connections that you see within this graph are actually dependencies between open source projects. And I think I'm done.
And time.
Okay, so
Thank you very much.
Thank you.
Now we have Mariana Damova from Mosaica, who will talk about ISME Hydro. And on deck we have Claudia Barancelli from OECD.
With this solution, we solve problems of water resources managers and higher officials with difficulties in decision-making because of disjoint data sources, inaccurately projected water levels with regards to droughts or floods, upcoming floods, avoidable management issues due to lack of data validation, or really very time-consuming reporting and summarization of the important data. ISME Hydro addresses all these problems and more because it combines all relevant water economic data with GIS, satellite imagery, and more, all in one place. It is based on a powerful e-infrastructure, mixing different flavors of AI for the purposes of monitoring of water resources of dams and rivers and their exploitation. ISME Hydro offers an interoperable open infrastructure that makes use of all necessary different kinds of information by using linked data technologies extended with intelligence that generates forecasts, formulates queries, throws alerts, and drives the communication with the users. Spatial information, remote space sensing information, symbolic and numeric data are put together via an ontology and produce a network of connected objects and enable knowledge discovery in explainable manner, XAI. For the forecast, we employ observation data of a variety of meteorological factors that influence the water resources conditions of dams and rivers, and apply them to neural network architectures along with in situ measurements to generate forecasts for up to 30 days ahead. With this, we obtain novel way to provide information, use superior interactivity, multifaceted visualizations, seamless extendability, effective maintenance, optimal utilization of Earth observation and in situ data, combined with geospatial information from GIS and other domain knowledge. ISME Hydro also supports data audit and user management roles. It is clear that water resources management can vastly benefit from the integration of Earth observation data with other relevant for their monitoring data in a web-based workflows. Listening to the presentations during this conference, I see that this infrastructure can be very easily moved to other domains, like, for example, the forestry domain from today in the from the keynote talk from yesterday. So we are ready to deploy this solution and provide a disruptive web-based workflow that makes use of a combination of AI methods and delivers a viable and hands-on solution with this powerful e-infrastructure for the benefit of water resources managers and beyond.
Thank you. So next we have Claudia Barancelli from OECD talking about the OECD Municipal Atlas. And on deck we have Jakob Nalepa from KP Labs.
Yeah, this is fun. So thank you for having me. I'm leading the OECD Geospatial Lab. OECD, for who from you does not know it, is the organizations for the economic and cooperation development. And we count 38 member states all across the globe. So we're really obsessed about producing comparable and timely statistics at ever more granular scales. So with this in mind, we have embarked in a new recent endeavor, building an integrated and harmonized database of granular data. In doing this, we want to, of course, allow for sound and robust international statistical comparisons. We want to integrate data coming from official statistics, but not only, data coming from unconventional sources, so sensors derived data at large, so not just Earth observation, the Earth observations ones. And of course, we want to do this rendering transparent all the effort that is going on behind the scene to the final user, who should be not only practitioners and experts, but also policymakers and policy analysts with less technical knowledge. As we heard before, we have more and more spatial and temporal granularity in the data that we have potentially available. This brings a lot of opportunities, but also a lot of challenges that we have to deal with. But to make my point and explain you why this is important, and it's an important endeavor, I'm bringing you 3 examples of indicators that are included in our database and exposed in our platform that can answer to some examples of policy questions. The first example is related to the geography of income levels and inequality. I know I'm going a little bit far from the topics that have been discussed so far, but it's an important example because it highlights how important it is to study this type of phenomena and these dynamics at increasing granularity, spatial granularity. And the city of Brussels brings some nice, unexpected insights about how incomes and inequality patterns intersecate with each other at local scale. The second example is about digital inequalities, again, looking at the metropolitan area and trying to find how good are digital services does not give a homogeneous picture. You have to go granular and you have to work with data coming from different sources. In this case, we're working with data provided by a private provider, Hookla. The third and final example is about the geography of housing demand. Many policymakers, they're wondering what is the impact of remote work and global epidemics on housing demand and how home ownership demand is shifting from places to other places with different characteristics. In order to answer this question, we have to work with data coming from satellite imagery to study changes in urban land uses and urban functions. We have to work with official statistics on income levels, and we have also to work with data provided by private sectors, for instance, on housing prices. So a lot of challenges, but we're up to the challenge and we're planning for it. Now, there are many, many different working areas where we are concentrating now. Here I'm bringing only 3 examples. First, we're consolidating our indicators and topics to be the most comprehensible possible. We are adding constantly new granular data and, whenever possible, also grids. Of course, we're doing this building a rather humongous database of metadata that is going to be very, very important. And finally, we are working on improving the user interface so that it becomes easier for the final user to find the right indicators that he or she needs in order to answer their policy question. Thank you.
Thanks very much, Claudia. Now we have Jakub Nolepa from KP Labs, The Beauty of Seeing Beyond the Visible. Followed by Justus Maja from CNRS.
All right, good to see you. We are all here having fantastic time at BiDS because we actually all care about the planet. We know that we struggle on a daily basis. We struggle with a lot of things like air pollution, we have deforestation, we have climate change. Those are serious threats to the planet, meaning that we need to act today because we want to have better tomorrow. And if we do not act today, then we are in a very bad shape fairly soon. And this is one side of the coin. And the other is that we actually have fantastic technology that could be used for having better planet and better future. And we know that we capture a lot of data in orbit. We can observe Earth. This data might be very highly dimensional, meaning that it is difficult to downlink this data back to Earth to analyze it on the ground. So perhaps it might be good to bring the brain just close to the eyes of remotely sensed data. We have satellites that could capture images that are of different characteristics. We may have hyperspectral data that would capture very detailed characteristics of the objects of interest, and we could try to extract some actionable items on board the satellite, meaning that we could just transfer the insights, not the raw data. And there are lots of potential applications of that kind of pipeline. For instance, we may want to detect methane plumes, we may track some objects, we may try to analyze the soil, because we know we need better farming, because this is also our future. And we can imagine that having in situ, on the ground measurements of soil to analyze it better and to understand it better, it is not scalable at all. So we cannot scale. On the other hand, we have remote sensing that offers enormous scalability, so we can capture a lot of data for a lot of areas around the globe. And we actually wanted to have something that could be used for better farming. So we could have some precision agriculture technology that could be used for improving not only crops, but also the quality of the soil. So we are trying to build something that could be used in practice. We gathered data which is on the one hand, we have hyperspectral data, and on the other hand, we have in situ ground truth measurements. And we wanted to build something that the community could use for building algorithms that are deployable on board satellites. So we prepared the data set that is super easy to download and perhaps utilize. You have all the information about the images captured for a specific part of the globe together with the ground truth, right? So you could build your own AI solutions and verify them in a real task, which is a downstream task for hyperspectral data. I actually have two news. The bad news is that we had the challenge that is already over, so we have the winners of the challenge, and they were fly on board Intuition 1, which is, I think it's going to be launched on Saturday if everything goes well. But there is also a good news. The challenge is still open, so you can just get into this web page, you can download the data, you could have the AI-ready data set, meaning that you have the training data, you have your test data, and you can easily verify how good you are in analyzing this kind of real-world data. You can submit your solution, see how you compare with other participants, and perhaps you could push the current state-of-the-art in soil analysis. We have 4 parameters of the soil captured for a specific region, but this could be transferable to other parameters as well. So you're more than welcome to download the data. You can, I'm pretty sure that you would submit your first submission in 1 hour, because we have a very nice open source, by the way, example on how to build the model, how to process the data, and how to basically submit your solution to the platform. So good luck, and hopefully you will enjoy it.
Thank you. So next up is Justus Margin from CNRS talking about DGGS and X-Array, a draft implementation, followed by Francesco Volo from Boku.
Okay, thank you. So in parallel to this conference, there's the OSGeo sprint, and basically what I'm going to do is I'm going to present the result of what we've been doing. So the group you're seeing, we came together and decided to get the tools we're working with to work with X-Ray, one of the core packages of the Pangeo ecosystem. And yeah, so I'm going to very briefly introduce both concepts. First, X-Ray is like a domain-agnostic tool, not just specialized on the Earth system sense, and it is a n-dimensional object that provides named dimensions, contrasts that with standard array objects that you would index using integer access offsets. So labeled arrays as well, which means that you have you don't index using integer indexes as well, but you would use the actual coordinate values, and you'd have like multiple variables and coordinates. So the standard way to represent positions on Earth is like the latitude, longitude coordinates. And the issue with this kind of grid is that you'd have distortion, very strong distortion towards the globe, towards the poles. The traditional way is to use projections, but those are only like distortion-free or like minimal distortion locally towards the projection definition. And so there's the DGS, which subdivides the Earth into like, or approximate using flat surfaces. Like there's 2 examples here. One is H3, which uses hexagons as the base face, and HEPX, which uses spherical rectangles, circular rectangles. And so the idea was to combine this concept with the X-ray tool, which was previously not possible. The result is this repository, so you can just search for XDGS if that is something that interests you. And so basically what you start with is a data set that's already in that system. You would have a cell index that is indexed using the standard pandas index. You would now use some API that we will improve so it's not as much of a mouthful. And you would get a specialized index, in this case H3. And with that, you would be able to select using latitude, longitude values, because that's the most user-friendly way to search things. Even though the latitude, longitude values are not explicitly available on the data set itself. We can get those back because the cell ID contains all that information. And yeah, so that is the result. Thank you very much.
Thank you very much, Justus. Now we have Francesco Vuolo on the Koala enabling platform for digital farming, followed by Valentin Presendorfer from the World Food Programme.
Thank you, and good evening, everyone. I think best definition for Koala is a family of scientists, a family of people with enthusiasm and motivation who managed to put together a number of algorithms that can help performing better agriculture, so sustainable agriculture. This is in fertilizing, in irrigation, or more in general, water management at larger scale. And here you have a list of examples of things Koala or the Koala family does. So why Koala? Why is that special? It's because we do it very fast. We produce these products very fastly, but still we maintain a high accuracy in what we deliver, and we track that accuracy and that precision of the data delivery. So some of us have even certifications or quality certification on what we produce. And the questions we answer, we help to answer are something like, shall I irrigate, if you're talking to a farmer, and how much water should I provide? And with Koala, we enhance the efficiency of the data production, the accuracy, as I said. We can scale, we can customize, and we can save on cost. So Koala is running on a cloud infrastructure, taking Copernicus data, and via OGG standards communicating to users, farmers, water managers, and broader community in the agricultural sector. We can make a test stress. You can scan the codes. This will activate a very complex processing chain. We take sentinel data, climate data, and process evapotranspiration. And the benefit of scanning it is that you also get that token that you can later use for further testing the application. At the end, you should get this image generated, which is a map of evapotranspiration for a given set of coordinates. What is very special is that you can parameterize here, for example, the reef resistance. For those of you who are agronomists, this is one of the parameters used in the ET, so evapotranspiration modeling. Has been used in Australia, for example, by this company, Prophet, and has been integrated, and better decisions can be now made on yield forecasting, or for irrigation scheduling. Schedule It is another company based in Australia. My colleagues in Italy, I'm using it for showing time series of data, but also for calculating evapotranspiration at district scale and providing this information to water managers who need to comply with regulations. But it's also been integrated as a plugin Quantum GIS, where myself as a scientist can connect to the data infrastructure and look at some of the data. So why I'm here today? What was the reason for coming here? Essentially, Koala is aspiring to become larger and bigger and grow and provide the services not only to the Australian partners and to the Austrian partners, but perhaps even wider, so Italy, Spain, and other countries. And we are running at the moment in a small computer that you see here on my left. We've been testing it on the Austrian EODC, on the Wikio DIAS, and I'm looking around for other possibilities to host this platform and be able to provide it to a wider community around the world, again, to perform sustainable agriculture. Thank you very much.
Thank you, Valentin. So next up, we have Valentin Presendorfer from the UN World Food Programme, talking about the humanitarian data cube, Earth observation data for humanitarian operations. And on deck, there's Aurélien Lac from Thales.
Thank you. I think over the last couple of days, we heard a lot of cool technologies and data and like theory. And I figured it would be also good to showcase an example where we can harness this technology for specific use cases. In our case, that is for humanitarian operations. I need to spend one of my minutes to quickly talk about WFP. Some of you might not be familiar with what we do. The World Food Programme is the biggest humanitarian organization in the world, and it assists 160 million people in 120 plus countries. That means then on any given day, there's more than 5,000 trucks, 100 planes, and 30 ships on the move, delivering aid to people in need. We also received the Nobel Peace Prize in 2020 that you might remember, and due to the current circumstances in the world, our work is again in the focus. So, moving on to the humanitarian data cube, what is it? Well, it kind of started out of the need to move our processing from on-prem to a cloud deployment. We work on a global scale, so all of our colleagues need data at different places and different points of time. So really try to process all of our data on a global scale and, for the full time series. Currently, the HTC is a fully fledged deployment on AWS, and we use all these technologies that you heard in the last couple of days. A shout out to Bangio. And we build mostly on these open source tools. Currently, we have more than 100 data products. Most of them are in the climate and land domain. Here I'm talking mostly about rainfall, anomalies, SPIs, but also in the land domain NDVI and land surface temperature. While most of these would you maybe consider pretty basic, there are some very unique data products that you wouldn't find anywhere else. You see these animations on the bottom left. These are NDVI on the left and LST on the right, which we filter and gap fill on a global scale. These are 1 kilometer data sets from MODIS for the entire time series that we store as cloud-optimized GeoTIFF on S3, ready to access. We're also assimilating ECMWF data, ERA5, and also the seasonal forecast to kind of add this forecast domain to our portfolio. I'm not going to go into detail on this slide. It's just to showcase how HTC is becoming really a central piece within WFP and the community that serves EO data to different systems and programs within WFP and beyond. The example I want to quickly show is what I call the admin level extractions. So we do extract data for rainfall and NDVI globally at admin levels 0, 1, and 2 and average them and serve them to an API. These are then served to users or other applications like the WFP Hunger Map Live that does food insecurity predictions and uses these as features. Or they can just go to this very nice little tool that we call Database for visualization. And here you can look at different growing seasons and see, for instance, for Somalia in 2011, there was a drought. And you can clearly see on the left, in the first season, there was a clear deficit in rainfall. And in the beginning of the second season, there is another deficit, which then you can see in a dip in NDVI. And here's a little map that showcases this kind of drought in the Eastern Africa region. But we not only keep this data to ourselves or serve it through the API, we also have a collaboration going with the United Nations Office for the Coordination of Humanitarian Affairs, OCHA, to prepare specific data sets that are tailored for humanitarian use. These are then uploaded to the Humanitarian Data Exchange platform, which is a one-stop data shop for humanitarians for their use. This really fills a crucial gap on the platform. There was prior no climate data available. In times of climate change and need for climate mitigation, this is really, really crucial in my opinion. So these data sets are really bespoke made for these actors, and they're very easy to use and provide a low entry level. These are CSV, is nothing fancy, but I think it's really important to also think about these stakeholders. Thank you.
Thanks very much, Valentin. Now we have Aurélien Lac from Thales, followed by Christian Racoton-Renib from Thales Service Numérique.
Hello, everyone. Can you? Oh, yeah, screen is good. As you may observe, I am not Aurélien, because he is currently in the airplane. So I have the very hard mission to replace him to the task of presenting the work we did in our research and development department on the subject of investigating the potential of diffusion models applied to remote sensed images, and especially two use cases. The first is rare object image generation, especially for semantic segmentation. And the other case was how we can exploit diffusion model for downstream tasks, such as semantic segmentation for open vocabulary, for instance. So my name is Louis, by the way, second on the list. I will not cover in this presentation the theory behind diffusion model, because Bertrand Lesaut did an amazing job about it, an amazing presentation, so we'll keep that. We rather be focusing on the approaches we made. The first was to train a foundational model to space, to specialize the diffusion model into, how do you make these crazy models able to work on space images? Then we applied some conditioning techniques, one method on shape, and the other more focused on the object we generate. That's the architecture we were using, stable diffusion, for those who know it. And the first test we did was using stable diffusion, not fine-tuned, to answer the caption, a remote sensing image of one plane. So here you can see we have indeed images of planes, but unfortunately, we don't really capture the remote sensing sense of the images. Our model, after fine-tuning, is able to do this, what you can see on your right screen. Also, after pre-training, we have a good control of generated object through text. As you can see, we are able to generate this kind of images. We can also do this kind of images. The important point here is that we can have modifiers and quantifiers in the description. For example, we are able to make a lot of harbors, small vehicles, and many ships. If we had written here few ships, then we would have an image with few ships. Another interesting property is that we can also generate landscapes that have not been seen during training. We never trained on kind of beach places, and as you can see, we have a neighborhood close to a beach here. That's the funny part. When training, we really make sure that we don't lose the generalizing power of the foundational model, which was stable diffusion at the beginning. So we really want to make sure we can inject the old concepts back in satellite images. So for example, we have those funny images with flowers, but we can also generate more realistic scenarios, such as a crowd dressed in red in a concert. We can also do inpainting, so that's what Bertrand just presented this afternoon. Can you guess which image is the real and which image is the false? Left, right? Right or left? Right? Okay. You're right. No, I mean, the real image is the one on the right. The fake one is the one on the left. So you're all wrong, basically. Then we had further conditioning, such as control net. And yeah, that's it. finally, we can do segmentation, and that's my last slide.
Okay, thank you. So now we have Christian Rakoton-Drainib from Thales Service Numeric on the overview of vision language models applied to remote sensing data. And after that, we will see a small demonstration of Gaia.
Hello, everyone. So I decided to make this presentation yesterday because I've worked on vision language models, and I decided to show you the capabilities of these vision language models when they are applied to remote sensing data. In short, vision language models are models that take both text and images as input and can perform a variety of vision language downstream tasks that I will show you. You should know that there are several vision language models, each working in a different way, but I'm going to show you directly the result we've obtained as we don't have much time. What I've done is annotate a dataset of aerial images in order to form a dataset of images and captions, and then we fine-tuned some open source models in order to get better models on remote sensing data, and we evaluated them on different downstream tasks. And for example, here is the kind of result we can get with fine-tuned clip models on our dataset. So if we evaluate this model on image retrieval, for example, here is what we can get. So basically, we give the model a textual request. So for instance, we can ask for a tennis field. And here, in fact, it returns images where we have tennis courts. You don't see it very well, but there is a tennis court here as well, and here too. We can give more complex requests, like here, for example, where we query buildings along quay in an industrial area, and so on. We also evaluated and fine-tuned models on image captioning. And here I decided to show you results of a model called BiDS'23 without fine-tuning, in order to show you that even without fine-tuning, this kind of model can have impressive results. So here we gave an image of an airport, for example, and here is the kind of captions we get in return. So here it recognizes an airport with several planes parked on a runway. Here it recognizes the Buckingham Palace, and I checked it. Here it recognizes a stadium, and it's even able to read the Real Madrid written on the top of the stadium. And here it can, for example, recognize different crops. What we did also is to compare different models that we fine-tuned on visual question answering. And we took, for example, the model Albef. We took our captions and we used large language models like GPT and Llama 2 in order to generate the data set of questions and the corresponding answers. And we fine-tuned our models on this data set. And we then get this kind of result. So here you have the different questions and the answers given by our models against the ground truth, which were generated by GPT and Llama 2, for example. So here we can ask if there is a road across the forest, and this is the kind of results we can get. And finally, it's not open source, but this morning I also tried to ask GPT-4 to describe an aerial image. So here it's an image of the Earth before and after the earthquake in Turkey in February. And this is the kind of response answer it can get. So it's very impressive, as you can see. It's able to detect changes. It knows directly that there are two images that represent in the same area, and it compares them before and after the earthquake. So here it recognizes the buildings and the clear streets on the left, and then it's able to recognize the shelters inside the stadium on the right and the buildings that are damaged, and so on.
Time.
Okay.
Thank you very much, Christian. That's really interesting. Okay, so we miscalculated, I think, the time a little bit. We have a little bit more time than what we thought we had. So next time, the lightning talks will be 4 minutes and 4 minutes and 7 seconds instead of 4 minutes, and that should bring it in. We have a little bit of time extra, in fact, and we will now get the demonstration of Euclid from Antoine Basset.
Okay. Thanks a lot to the organizers for allowing me to show this crazy images from the Euclid satellite, which was launched in July, and those were released yesterday, so first public color images just for you on the big screen. Thanks.
Okay, so thank you everyone for sticking around for the lightning talks of BiDS'. If there are any questions on the Euclid mission, I'm sure Antoine here is happy to answer them.
Sure, but I am no astronomer, so.
No worries. But maybe we do this basically outside. For the in the events of the cocktail reception or the code sprint dinner. So with this, thank you very much for joining us also on the second day of BiDS'.